Okay, so I'll start. So I hope that at the end of this meeting, everybody can hear me, by the way. You can.
Yes.
Yep. Okay, so I hope that you will be able to understand the encryption protocols in Matrix, how group encryption works, why you can access encrypted history, because this is strange, why sometimes you see unable to decrypt, and how you can help the dev team to fix that. What is key gossiping, what is verification, and why we do that. And also I will talk about key backup and secured storage at the end. So I will start with the basic definition of E2E. So you all know it, but basically it's a system of communication where only the communicating users can read the messages. So no one else, not the internet provider, not the app maker, not the server, no one. So for that in Matrix, you may have heard about the famous Allman and Megolm. So Allman and Megolm are both encryption protocols that provide E2E. So Allman used for devices to devices messages, it's the double ratchet, and Megolm is used for group messages. It's a simple ratchet. But of course, what the hell are ratchets? I will explain that. So basically, at the beginning, there was no ratchets. So it was just plain symmetric encryption. So in symmetric encryption, we have a shared secret key that is used to encrypt and decrypt message. It's pretty easy to visualize. So basically, we have a set of indestructible boxes that can only be closed open with the key. So Alice and Bob have both duplicate keys. And if Alice wants to send a message to Bob, you put the message in the box, you close it, you send it via mail, and then Bob on the other side can have it and open it. And no one in the middle can open it. So it pretty much looks like that. So you see I have, just checking if my face is not covering. It's covering a bit, it's annoying. I will shut down my face. Okay. So basically, Alice has something to write. You put it in the box, you send it. There is one thing interesting to see here. It's the key. We both have the same key. It's problematic. How do we do that? Because we would have to meet in person, exchange the key. So it's annoying. And I have to talk about that right now because it's an important thing to understand. So it's called the key exchange problem. So Alice and Bob both have a duplicate key, but how do they do that? How do they do that without meeting in person? So yeah, of course, they don't have to meet in person. There is math for that. And as promised, I won't talk about math. I won't do math. So it's called Diffie-Hellman. So it's a way to jointly establish a shared secret over an insecure channel. So it's easy to visualize with colors. So instead of talking about case, which are numbers, let's imagine it's color. So the goal here is that we want to agree on a common secret color on an insecure channel. So the start of that is we each start by choosing a secret color. Okay, so Alice has that reddish color and Bob the bluish color. I'm Daltonian, so sorry if I'm not using the correct color name. So the idea is at the end, we want that our secret color is kind of a mix of these two secret colors. But of course, I cannot just send my secret color on the unsafe channel because you will be able to see it. So the trick here is that we agree on the common color. Here it's the yellow. Okay, so we know both the common paint and we have our secret color. And what we are going to do is we are going to disguise our secret color before sending it. So you see here, Alice will mix her secret color, but will give that orangish color. Bob will do the same. And as you can see, there is no way to guess what was the secret color because you cannot unmix color. So we send that to each other, and it's like magic. If I add back my secret color to the disguised color of the other user, we end up having the same color. So that's how it works. We are able on an unsafe channel to create a common secret. I mean, if we look more closely, this common secret color here is a mix of that and that. So basically, it's red plus green plus yellow, and it's the same here. It's green plus this, that is red plus yellow. That's why we have the same. And if someone on the line is trying to mix these two, you will have a different color because there is too many yellow in that. So let's go back to here. So we have our end-to-end channel, we have the common key. So we agree it's pretty solid now, yeah? What can happen? Let's go back to the digital world, and we have now Mallory. So Mallory is listening into the line. So now we don't have boxes, it's like bytes, and we have the key. So what Mallory is doing is recording everything you're sending. It still looks safe, you agree, because yeah, Mallory do not have the key, so basically he has a useless pile of bytes. But what if at some point in the future, Mallory is able to take Alice's key? So this happened when you got hacked, or you clicked on the wrong link, or someone accessed your phone, something like that. So we can see now that Mallory has the key, as well as all the previous message we sent. So now Mallory can read all the messages we sent since the beginning, and worst, he will be able to read all future messages. So you see, we were from a situation we thought was pretty solid and safe, and it's not at all. Security is always, it's important to understand that, is that security is here to mitigate when something bad happens. It's always the case. It looks like you don't need it, but if something bad happens, if you don't have security, you are doomed. So that's when the simple ratchet tags in. So the goal of the simple ratchet is to prevent Mallory from being able to decrypt messages he collected if ever he managed to steal the key later. What's the idea behind that? So the idea is that now, instead of using always the same key to encrypt messages, we are going to encrypt every new message with a new key. And the trick here is that the new key is computed from the old one. So basically, we have that blue key called the root key, and I would be able to compute a new one from that one, and using a one-way function. So what's a one-way function? A one-way function is a transformation that is easy and quick to do, but very hard, technically impossible to reverse. So sorry, there is some math here, and I promise we won't do math. So I can explain it simply. So let's say that we don't have the key. The key is the word, okay? And this is my one-way transformation. For a word M, you take the definition of that word in this dictionary. Now you read the definition and you take the third word of that definition. We have now a new word. So we have a transformation from an old word to a new word. And you would see that it's irreversible. So for example, I have a secret word, and I searched for the definition, and I took the third word of the definition, and this word is processing. Can you find the word M? Yeah, you see what you have to do. You have to take the dictionary, read every word, and check the third word of every definition and see if it's processing. And there might be several words that will have the third word that is processing. And notice that it's very easy for me to make it more complex by doing some iteration. Let's say I take the definition of the word, I take the third word. Then that third word, I search for its definition. Then now I take the first word of the definition. Then I take this word and I search it again. You see that it's easy for me to do it, and it's very hard to do if you want to find a word. So by the way, the answer is vector. If you look at vector in that dictionary, it's a quantity processing buff match. So processing is the third word of the definition. So let's now use the simple ratchet. So we have Alice and Bob. We agreed on a root key. That would be our secret word. So I use it to encrypt the first message. Now I apply my transformation one way to get the new key or the new word, and I encrypt the second message with that key. And I do that again, and so on and so on and so on. On his side, Bob has the same root key, it can decrypt the first message. You just have to do the same transformation. So this is called ratcheted key. So we have the root key, the key index 1, the key index 2. We ratchet the key. And I am able to decrypt the key. Also, we can delete the previous keys. We don't need them. So they are often called temporary keys. So by the way, that's why it's called a ratchet. It's easy to go one way, but you can go on the other way. Let's see now why it's better. We have Mallory back. He's listening for everything. So he has been able to capture the 3 first messages that were encrypted with root key, key 1, key 2. And let's say now that Mallory, again, is able to hack Alice's computer. He will be able to get only the 3rd key. You remember that we deleted the previous one. So what happened now is that Mallory is not able to decrypt previous history because you cannot get the previous key from the current one. So you can see it's a lot better. Mallory is still with an endless pile of bytes and can do anything. On the byte side, there is no post-compromise security. That means that Mallory will be able to compute the following keys. Of course, it's easy. So it will be able to decrypt all future messages. But it's already better than no ratchet. But what if I told you we could also have post-compromise security? And of course, you guessed, it's the double ratchet. So to explain it, the idea is that we are going to add a variable when ratcheting the new key. So with the simple ratchet, it's a constant. You remember with the word analogy, we take the 3rd word of the definition, we have the new word. We take the 1st word, we have the new word. What if now we change that? Let's say we start with the 3rd word, and at some point we change. Now it's the 2nd, after it's the 5th word. So that's what the double ratchet is doing. Of course, the issue is that when Alice changed the word to use, the number of in the definition, Bob must do the same on the other side. So the thing is that we have to agree on the new secret, on the new variable to inject in the ratchet. And again, we do that with the color trick. So basically, when I send you a message, I also send you this guy's color. And at some point in the future, you reply, you send me also this guy's color, and then we mix that, and we have the new color that we inject here. So let's see what the impact, the consequences for Mallory. So Mallory has the key index 4, let's say. It cannot read previous messages. It tried to read the new one. But the thing is that at some point we are going to change the variable, and Mallory won't be able to know what is the new number we are using, because he won't have access to the secret colors, only the public colors. So if Mallory is lucky, he will be able to see 2 free messages. But most of the time, he would only be able to have 1. So that was a lot of complex things. So let's have a bit of fun. So I will start with some naming fun. So these are the crypto salamanders. So you can see these 2 cuties. So this is an axolotl, and this is an olm. So that you know, the original name of the double ratchet was axolotl. So the axolotl is incredible. If you cut an arm, you remove an eye, it will grow a new one. So it is not healing by scaring, it's capable of regeneration. That's basically what the double ratchet is doing. If it's compromised, it will fix itself, it will regenerate. And this one is the olm. So it's another salamander that you can only find in Europe. So maybe we will have to ask Matthew who came with the name olm. So let's go back to some crypto. Let's talk about group chat. So we understand now what is a simple ratchet, what is a double ratchet. We see that the double ratchet is superior because it can regenerate itself. But how does it work when we start looking at groups? Let's look at this setup. So in this setup, we have 3 persons. we have established E2E double ratchet channel between each of us. And now if I'm Alice and I want to send a message to that group, with this setup, I will have to encrypt the message twice. I will have to send it first once to Valere and the other time to Bob, because that's how the E2E channel works. So it's nice, it's working, but what if we have 30 members in the group, and if each member has 2 devices, like a web and a mobile or more, we can see that quickly for one message, we can end up encrypting it hundreds of times and then sending it hundreds of times. So now imagine it's a video and not text. You have to send the video hundreds of times. But it's working perfectly. And by the way, that's what Apple iMessage is doing when you send a message. And also, if there are developers here, did you know that you can do that in Matrix, actually? If you create a room and you use the dev tools, you can set up the encryption algorithm of that room to all. And if you send a message and you click on view source, you will be able to see that this single message has been encrypted several times, one time for every device in the room. It's also, I think, interesting for you to see that A is transformed in all of that characters. So that's what an encrypted message looks like. So can we find a better strategy for groups? The first thing you could think of is if we create a shared group key, the same way we do it when we are 1-1, we agree on a shared key. Can we do that for the group? So every person in the group uses the same key to send message. It would be a lot better with bandwidth, of course, that you just have to encrypt once and then the server fan out the same message to everyone. The issue with that is the key exchange problem. How do we establish the secret key? So technically there is math for that. So it's like a multi-party Diffie-Hellman. It looks like a huge binary tree. We don't care about that. The thing to remember is that it's complex, so it's taking time. It also needs synchronicity, meaning that everyone has to be online at some point so that we agree on the shared key. And what happens if the group key is compromised? Do we have to do that again periodically? And again, it will take a lot of time. So it's not practical to do that. The other solution is the sender key solution. Instead of having one group key for everyone, here, every member of the group creates a sender key. So basically, so Alice will create a sender key for her in this group, and Alice will distribute that key to everyone using the existing E2E channel. And after this setup, Alice will just send the following group message encrypted with the sender key. So basically, everyone in the group has a sender key that you share to everyone. Let me show it in these slides. So you see the first thing, Alice creates a sender key. Then I use the home channel to send the sender key to everyone. For developers here, it's what is called a two-device m.room key. So you see I'm sending the key, it's encrypted end-to-end to Valere and to Bob. They can get it. So now everyone has Alice's sender key. And now Alice encrypt her message with that sender key. So the same message will be fan out to everyone. And as everyone have the key, they will be able to read it. So you see, there is an initial burst where you have to distribute your key to everyone, but after that, it's quite fast. Also, the sender key is a simple ratchet. So this key, basically, when I'm going to send the second message, I'm going to ratchet it with a simple ratchet. So this is my root sender key, and so every new message will use a new key. But it will be fast because we don't have to exchange anything. Everyone already has the root key. So let me sum up group encryption matrix. By the way, everyone in matrix is a group, even if it's a DM. Because let's say if I have two devices, you have two devices. For the crypto layer, there are 4 people, 4 entities in that room. So it's already a group. So at the beginning, when you start typing a message in a room, you have to set up a one-to-one OLM double ratchet channel with every device in that room using the color trick. After that, you create your sender key, you share it to everyone. All the other group participants are doing the same. And then after that, each participant use his sender key to encrypt. Maybe you have noticed the first time you send a message in a large encrypted room, it's taking more time to be sent. So it's all these initial setup files when you have to download other device keys, establish the home channel, and then send to everyone. And after that, it's fast because everyone already have the key. As always, Matrix is great, very great for developers. You can check it by yourself. If you are in a group, in a room, let's say here there is a room with Alice and Bob. Alice sent 2 messages, A, B, and Bob replied to C. You can look at the source, and the important thing to notice here, it's a session ID. So basically the session ID, it's your sender key ID. You can see that Alice, the 2 messages sent by Alice are sent using the same sender key, and Bob is using his sender key. And if you look closely, I'm going to show you because we can, you see that these messages, they all start with AWG. If you turn that into X strings, basically 3, it's the Megolm version. So the version of the protocol. 8 is just saying that the next thing is an int. But you can see that this one is index 4, this one is index 5. So you can see that the ratchet index is growing. It's the same key, but ratcheted. So this one was 4, 5, and next one sent by Alice would be 6. When our Megolm session rotated, because we are going to change them, so that you know every week or every 100 message, you will change your sender key. Also, if a device leaves the room, why we do that? Let's say that a device or someone leaves the room, we don't want him to be able to decrypt future messages, because currently he will be able. He has the ratchet. He has my sender key, so he could ratchet it for a while. So when someone leaves, everyone in the room rotate his key. So there is again this burst. You can also manually trigger it if you use Discord session. So it's a command line. I'm showing it because it might be helpful. Let's say that someone is writing to you and you cannot read his messages. You can ask him to enter this command so that he will then create a new key and send it back. So it can help you fix issues if there is like an emergency. Of course, before doing that, please send a race check so developers can see what did happen. Quick code, why don't we rotate when someone joins? I'm talking about that because it's helping to understand the ratchet thing. Because actually there is no need to. If someone new join, I will have to send it my sender key, but I don't want him to read previous messages. So what I will do, I will not send him my root sender key. I will just send it the last iteration of my sender key, so my ratcheted key. So from that ratcheted key, it will be able to go forward, so read the next messages, but not the previous one. So practical work before you all fell asleep. Based on what you learned so far, do you have an idea what did happen here? So there is a message in the room and it's saying, unable to decrypt. The sender device has not sent us the key. So what happened here, I will explain that this message was encrypted with J sender key. So he sent it to the room, but he was supposed previously to send us that sender key. So the issue is that we didn't receive the sender key. So if I go back here, so G sent the message, but it didn't send me the key previously. So therefore I cannot read it. So why is that? More important, why? possible causes. So we have an issue with our E2E channel. It's not created, it's broken, or the channel is okay, but we didn't receive the key. I don't know, maybe it was lost in transport, maybe it was not sent in purpose. I will give you some example of legit reasons. First one is that it's history. So I was not in the room when the message was sent initially, my current device at least. So that means it's expected that I cannot read it. I will be able to read next messages, but not this one. Another one is federation lag. So I'm talking about it because matrix is federated. So it's something we have to take into account. So basically, if Alice and Bob are not on the same home server, if Bob log in a new device, it will be on his home servers. And the home servers, sorry, I will put back I'm doing gestures for nothing. I'm adding back myself. So Alice is has her home server and Bob also. So Bob login on his home server. So home servers are to synchronize somehow to say, hey, Bob has some new devices. But at that moment, Alice started typing. So when Alice started typing, she was not aware that Bob had that other device. So she was not able to send him the key. So this is something that can happen. Oh, sorry, I have locked my computer, so I lost everything. Let me share again. Okay. So other buggy reason, of course, there could be a lot of buggy reasons. So the home server didn't deliver the home message to me, the two device message. Maybe you are on some new implementation. Maybe my device has had some outage when sending the key. I was in traffic and had no network. It retried but failed. The home channel are out of sync, or other. I mean, my device was not up to date with all the members in the room. So there are a lot of buggy reasons. Maybe you've noticed that I've said that I can't read history when I'm logging with a new device. And I guess that, of course, you tried that and it was working. You log in with mobile, and then you were able to see what was in the room. So why you can access encrypted history? So it's what is called Megolm key gossiping. So we are going to zoom out regarding the channels and all that. But what you need to know is that every element client have like a local store of the root key, or not always the root keys, but let's say the simple ratchet, the Megolm ratchet. So let's say that for room A, I have all the keys I need to decrypt the messages. This is configurable, of course. Some client can decide to store nothing. So what happened when Alice logs in a new computer? Alice logs in, then open a room, and then it's not. Of course, Alice is not able to decrypt because the store is empty. She had no keys at all. So what happened is that your new session is going to do a request to your existing session. So for developers, it's a two-device room key request. What happened here is that when received, your other session will say, oh, okay, I will share it to you. So it will share just the key you requested, basically, and then you will have them in your store. So that's why you will be able to see history. This is very great, we agree on that, but isn't it a bit worrying that my session are giving away keys like that? Yes, it is. That's why we have verification. I'm going to do a bit of history. So in the first iteration of the matrix, when you were adding a new device, the existing ones were prompting you to accept to share or not. So let's say you log on your mobile and then you open web and you see a lot of pop-up. Oh, this new device is requesting encryption keys. What do you want to do? Share, verify, ignore. So it was a bit annoying and also a bit fishy. I mean, sometimes you could be tricked into share. So nowadays you can verify your device. So that will make this key sharing process process automatic for your verified device, and never for others. It won't ask you again. So if you log in a new device, you verify it, it will automatically get the keys from the other session. But what does that mean, verify my device? I mean, we agree, I can see it's my device. I just logged in. How can it be mine? The fact is that the only thing you're sure of, I will remove my picture. I don't know how to move it. The only thing you are sure is that the channel is encrypted from end to end, but you don't know who is in the other side. So here, basically, it could be that there's a man in the middle. So simply, Mallory is in the middle, so you have an encrypted channel, you send the message, Mallory decrypt, read it, encrypt it back, and send it. It's easy to do with the color trick, you know. It's easy to do a man-in-the-middle attack in the DFM. You send your disguised, I intercept it, send you my disguised. So that's how I'm able to do that. Who could perform this attack? Obviously, your server could do it. It's very easy for your server to trick you. And when my device is asking, what are Bob's keys? I will say, oh, this is Bob's device, and it's a fake device, and you're doing the other thing for Alice. And actually, in your favorite app right now, I don't know if you're using WhatsApp, it's very possible that every time you create a group, a silent spy device is added. And how can you be sure? Because everything is closed source. So that's why we can perform verification. So the verification is a process that allows you to check with a visual representation. It can be numbers, or in WhatsApp or Signal, it's like a kind of graph with squares and colors. And it represents the identity of the current encrypted channel you are using. So if you don't see the same thing on both sides, you are man in the middle. So here I'm showing a matrix emoji verification. This is a bit smarter. I don't know. If you look at the WhatsApp code, it's like a very long string of characters. And often we only look at the three first and the third last characters. So in Matrix, we came up with an interactive way of doing that. So basically, you only have to verify 7 characters and without compromising security. And we turn these characters into emojis. So if there is someone in the middle, you won't see the same emoji, basically. So that's why you verify. And you have to do that, of course, out of bound. You cannot just take a screenshot and send it in the room where you are doing the verification. So in Matrix, after cross-signing, we started some verification party. I'm going to show you what it looks like. Sorry, I lost everything again. So it was out of one. We were on the call sharing emojis.
I'm going to hit you with a verification. Robot, mushroom, rabbit, fire, bicycle, fire.
It's like a break
Some elephant, banana,
in the talk.
Dog.
Chase, bicycle, instead.
So basically, we did that all the afternoon to verify everything. Let's go back to the gossiping. So now you can see that the old device will only send you the key if you are verified. A common misconception, we heard that quite often. We see people, hey, I am getting unable to decrypt errors, and I have verified the user. Technically, verification has no impact on the fact that you can or cannot receive encrypted message. Something else is broken. I mean, if you don't verify, you will still be able to establish E2E communication. What happens is that eventually one of your other devices is saving you because you are asking, hey, do you have the key? I didn't receive it, and it will gossip it. I put an asterisk here because, of course, there are some options where you can say that you don't want to send the key to unverified device, but it's quite rare. and it's not on by default. A quick word on cross-signing. Verification here, you see you have to verify every ARM channel. So if I'm in a room with 5 people, each having 3 devices, I will have to do 15 verification. So with each of their device, then they will have to do the same with all the other persons. So it's awful. So cross-signing allows you to do a lot more verification. You just have to verify users now instead of devices. And if I add a new device to my account, I will verify it myself, making it trusted for the other one. So basically, you will know if there is a ghost device on your listening to your groups if you properly verify everything. So it depends on your threat model. Not everyone has to engage in verification, depending on who, the threat model. A limitation on K-gossiping. Let me check the time. Oh, it's taking long. If you have no existing session or if it's offline, you won't get anything. I log in my new device. I'm asking the keys to the other devices. They are logged out. They are not online. So I won't get any key. So a quick practical word. I'm going to go fast on this one. You might have noticed that when there is an enable to decrypt, you see this request encryption keys link. So basically, this is doing that. So when I click on that, it's asking my other session, hey guys, I missed that key. Would you please send it to me? So that's what it's doing. It's requesting the keys for that message. So to sum up, Megolm keys are requested incrementally by new session while you scroll in a room, and there need to be another open session with the requested key. So this is annoying. So I will do a bit of history. At the beginning, if you wanted to have all your history, what you had to do was to export all the room keys manually into a file and save that somewhere. So if you lost your device or if you create a new device, you are able to import everything back. The annoying thing about that is that you have to do it periodically, because if you start a new chat, there will be new keys, and you will have then to export again to save everything. So that's why when Megolm key server backup was introduced. So it's a way to do that automatically. So basically, every time there's a new key, you will upload them to a server backup. It's safe, protected. You need a passphrase. So if you log in a new device, and I will show it here. So I have my existing session. I enable key backup. So I will back up all my keys. It's protected here. It's very strong encryption. So the server cannot read them. And if I have a new key, I start a new chat, or someone someone is leaving a group and we rotate the key, I will have a new one, and it will incrementally keep it up to date. And when I log in my new device, I could hit the restore from backup. So it will download the backup. I tap my passphrase, and I have all my keys. So this is a great improvement to the key backup. So I'm adding that one because I think it's often asked. So I talk about Megolm, key backup. And now we have another thing that is secure backup. What's that, and how is it related to key backup? So again, if I do a bit of history, first was introduce the key backup. So we had like a new secret known only by clients. So it was the passphrase, basically. The server had the encrypted backup, you had to decrypt it. So you had to enter a passphrase. Then we introduced cross-signing. And with cross-signing, we have 3 new secrets. So what do? Do we add a new passphrase? Imagine you will have your password, the key backup passphrase, then your cross-signing passphrase. So it's helpful. So that's why we created the Quad-S. So it's a generic safe that is server-side. So it's a standardized way of storing client secrets. So you can hold any kind of secret. It's protected by a master passphrase, the only thing you have to remember. And all your session can access your server safe. And more, what is nice is that there is also a protocol that allows your trusted sessions to exchange secrets that are in the safe. So yeah, basically it's an indestructible box with secrets inside. And again, you can see it. If you use the dev tool and you explore the account data, you can see that. So this is your online safe. You see that there are the cross-signing secrets and your Megolm backup. And what's the difference between a security key and a security passphrase? At the end, it's always a security key. In fact, a security key is 265 random bytes, and it's very hard to remember, even if you put it like that, represented as character. I think it's something like base 58, I don't remember. But the trick is that if you have a passphrase, in fact, your passphrase is transformed into a key, a pass key. So that's why I'm saying that at the end, the crypto layer is always using a pass key. The trick for that, it's called key stretching, or it's password-based key derivations. So the idea is that we have a passphrase that is easy to remember, but often predictable and shorter. And yes, we have this very random thing which is hard to remember. So the stretching process is taking time. So this is what is making hacking it hard. I mean, if I want to try every password, I will have to stretch every password before trying it. And the stretching process will make it very hard, quite as hard as trying every random bytes. Okay, so I think that's it for the presentation so far. I don't think I'm going to go further than that. So if you have any questions, I will send you the link to, I want to do that fast so I can have a quick reply. Of course, I've lost the link to the, did you learn something, basically? Do you understand cryptography better?
Yeah. On my side, it's really pretty good to know this. I have one question for you, Valere. On my case, I generate a secret key for the codes, and I don't have a passphrase actually. And if I understand, it's not possible to back with a passphrase, right?
But, so you, what, tell me again, I was writing a message. So you, what do you do? Can you repeat, please? I was typing something and
I use a secret key for my codes, and I don't have a passphrase actually here. Yeah. If I understand correctly, it's possible to have a passphrase. I need to run
you have to
crash
reset,
it.
Yeah, you have to reset everything. Remove the existing key and use a passphrase.
Okay.
Yeah. So I think that expert users are very fine with the passphrase. But for other, we told them, oh, this thing, you should save it somewhere.
Yeah.
They do it. But it's the same. Or they forget the passphrase, or they forget where they save that key. But as long as you have your device, basically you're fine. The problem is that if your device is broken, all the secrets that are only on the phone are lost.
Yeah.
So you need that to recover when you lose your phone.
Okay.
What are regarding this passphrase? We can see that some customers are asking for requirement to generate something like actual passphrase with dice or whatever. Where do you think we could do that? right? Basically, just use the passphrase mechanism and generate something with some algo client side, something like that.
So the what do they want? They don't want the passphrase, or they?
So they want a passphrase, but they want something generated, however, something that is not really rememberable, but at least that have a meaning, which means something with dice or something like that with a dictionary, basically.
Of course, the best thing is to let everyone generate a passphrase and remember it. But we have some customers that want the server admin to be able to send you back your passphrase if you forget it. So it's
so it's
something feasible. So basically, the on-server admin can say, "Hey, this is the passphrase for this user, and I will take care of it."
Okay, so it's less that, it's more than they want something that is writable, basically, and people can't mess up easily by writing it, I guess. More something like that, and that will be generated, because if you let the user put a passphrase, it will be for alphabet ABCD.
Oh.
That's
We've seen that with the stretching, it's not that bad. It's doing like a
yeah. I mean, if you know the seed, you can brute force whatever this. So
yeah, it's better than no security at all. So yeah, but we can let user put whatever they want, whether it's simple.
I was just thinking of a way that we could do it.
You could propose something. We could
Yes.
actually, yeah.
So
it could
instead
be
of
car, bird, yellow.
So you think the best is to just do that client side?
Yeah,
Okay.
totally possible.
Thanks.
I'm curious how many keys we store in the backup, or how far do we go? So if I understand this correctly, you're in a group chat and you have your sender key, and then you keep ratcheting that, right? And in order to read your history, you need to have access to the ratcheted versions of the keys, right? So does that mean we store everything, or can we recoup them somehow?
Yeah, my key backup is several tenths of megabytes. So yeah.
Okay, so is that sustainable? Is there any? Do we need to do anything about it eventually?
If you have the key backup, definitely we could at some point clean what we have locally and request it when we need it. Actually, the key backup API is very powerful. You can request per room. That's not what we are doing. Now we are downloading everything at once.
Everything, yeah.
So if you have a big account, it's taking 10 minutes to download and 20 minutes to add all the keys, and we don't have progress on that. But yeah, the current element clients are storing all the keys and, as early as they can. So the root key, if they can, other than that, the indexed key they have.
Yeah. And about discarding sessions, can you forcefully invoke that too many times and create problems on big groups? Or does the backend or the clients prevent against that?
It's affecting you mostly, because you're discarding your key, you have to send it back, and this involves downloading all the keys of the devices in the group. So you download keys, then you do the triple Diffie-Hellman actually, and then you encrypt that key every time, and you send it. So it's affecting you mostly.
Yeah, mostly on you, yeah.
Yeah, well, of course, it's doing a burst of message server side to device messages. So if you go into Megolm test home, huge encrypted room, and you start discarding session, it can have an impact. I'm doing it often.
Okay.
Thank you. That was really helpful and interesting. I'm Andy, by the way, anyone who hasn't met me yet. There was a vulnerability disclosed, I think, a week or two ago.
Yep.
Now, was that to do with gossiping the keys?
Exactly. So this one was a particular gossiping case that is quite new. I talked about gossiping between your devices. This one is when, for example, you send me a message and I didn't get the key, and I will send you a request. So, I don't send it to my devices. I send it to you and asking, hey, can you resend that key? Can you send it to me? So what happened here is, let's say that your home server is compromised, or you don't trust it. So the home server, it will wait that I log out one of my device. So, I log out one of my device, then it will create a new ghost device with the same name, code, it's a code, not a name, and then it will send you a request, hey, would you share this key with me? What your client is doing is it's checking, did I already share that key to this device? And if yes, okay, I already did it, so I don't know what happened, but I will send it back to you. Because we were just checking the device name, it's not the name, but the device ID, and not his real identity key, which is a cryptographic thing. So basically it was tricking you into sending the key of that message to a fake device. So he was able to to exfiltrate your keys by masquerading an old device. So that's how it was working. And if you want to know more, this was added. So this case, when you ask the sender to send you back, it's something that was done when typically I have my device, I've done a backup, then it fell on water, so I buy a new one and I restore it from my backup. So when I do that, I create like a clone device, but it has a very old version of the ratchet. So now the ratchet is broken, and yeah, I might want, hey, can you resend me the key? WhatsApp is doing that transparently. If you lost your device, the new one will ask you to re-encrypt because it has to be encrypted back again. Yeah.
Okay.
I think I sent a link and I put a widget in the room. If you know if you see it, or did I? Yeah. If you have 5 minutes to put comments in that.
I have another question, Valere.
Yeah.
You said you use a user in the group send on each user the sender key. And if I understand correctly, it's not the user, it's the session. If I have two sessions on two devices, I send two sender keys.
Yeah, it's in cryptography, there is no concept of users, it's devices. Like, yeah. So every device has a sender key for that group. So guys, I think we can wrap it up. Thanks everyone. Another last question?
Yeah, one last question about secret storage and restoring it. Because I have a lot of sessions that I have logged out of, there keeps growing a list of, this is like an unverified or like an untrusted, an unknown session from, I'll send a link, an image in the chat of messages where it says, like backup has a signature from unknown session with ID. But it's only 4 sessions and I've logged out of many more sessions. Is there something wrong with those 4 sessions, or is that expected for all sessions that you've signed out of?
So I think it's when you go to in the setting and see your key backup, the Q&A, that one, okay, I can see it. So you remember I said that with automatic key backup, you were sending incrementally new key as you get them. So this is using asymmetric encryption. So basically, you need the passphrase to read what is in the backup, but all your session, you don't need to enter the passphrase to add secrets. So so there is like there is a trusting. I'm trying to so when you log in, you have to know if you want to upload your new keys to that backup, you must trust it. Because if your home server is adding a backup to trick you into uploading all your keys, so you don't want that. So before starting uploading your keys, you want to trust the backup. And how you do that? So you look at who, every time you on a device you use the backup, this device is going to sign it. So basically, if a device you trust has signed the backup, you're going to trust it. But yeah, the general idea is that there would be an endless list in that. Every time you log in, log out, and you for some time you start uploading keys, it will add a line to that thing. So it's expected. And the thing that your device now your device is using that to know if you can trust that to send key. But yeah, this could be hidden, and it's a bit different now because if you enter the secured storage passphrase, it trusts automatically. So you don't have to look at all the signatures. Yeah, but it's just to define if you can trust that backup to upload keys to it.
Okay, thanks.
There are a lot more I could eventually add things on the backup because there is this asymmetric thing, but it will soon change. Yeah, because it's problematic. I won't go into. There is a possible kind of attack. Any other question? Feel free to ask question after. I can reply in the room. Thanks, everyone. I hope it was not too boring.
Thank you. It wasn't.
Thank you.
Thanks.
Thank you.
Thank you very much.
Thank you.
Thanks.
Bye.
Cheers.